engineer working for sevenbel. And today we will be taking a look at how to engineer quieter HVAC products by using acoustic imaging technology. We will start by introducing how acoustic cameras work, what the state of the market is, and what the benefits are when we're trying to develop HVAC products or optimize them. But the main dish or the main content of the webinar will be the applications. We will cover three specifically. We will start by trying to localize noise issues on a heat pump in a lab context. We will then switch to an emission problem on a residential property. So trying to assess the impact of the noise of a heat pump from the perspective of a neighboring property in a residential area. And we will finish with a bit more of a detailed use case where we investigate an automotive HVAC and try to characterize the sources in it, try to understand the spectra that each component is radiating, etc. So a more in-depth or technical analysis. Okay, so at the end, we will still save 15 minutes or so for a questions and answers session. So don't hesitate to write down your questions or type them into a Q&A box at the bottom of your screen. Okay, let's start introducing what acoustic cameras are and how they work and what their limitations are. So all the systems that you see on the left are commercially available and they've been in the market for a while. And that's how traditional acoustic cameras look. So they all consist on a 2D array of microphones that are placed on a surface. And by comparing the phase of each of the signals that the microphones gather, we are able to understand where the sound was coming from. So there is a difference in time of arrival for the microphones on one side or the other of these antennas. And based on that time of arrival difference, we managed to understand where the sound source was located. It's a bit more complex than that, but of course, all the systems work on beamforming, which are variations on this concept. There are two performance factors that you need to understand when evaluating acoustic cameras. The first one will be the size of the instrument. So larger cameras, larger microphone arrays will perform better in lower frequencies. The lower frequency cutoff of the instrument is determined by the size of the array. So the longer the array, the lower the frequencies that you can measure. Aside from that, a larger array will also be able to be more precise at any given frequency. So for example, a larger camera at 1000 Hertz will be showing the sources in a more compact way than a smaller camera. The second parameter that's critical is the amount of microphones that the systems have. So a smaller camera with less microphones will not have the same available dynamic range, meaning it will not be able to show you high and low level sources in the same picture. So again, more microphones is better for the dynamic range or the ability to show low and high level sources in the same picture. Basically, to recap, we want a large array with a lot of microphones. The problems or the limitations of these technologies, they all work really well, they perform really well, but they are usually very heavy, extremely pricey, sometimes mains powered, and they are usually expert systems. They take a long time to set up, and there is a steep learning curve to know how to really use them. On the other hand, the point and shoot cameras, like the smaller ones on the bottom of the screen, also work really well. They are easy to use, but they are very limited in terms of the frequency range that they can localize and the amount of sources that they can show in one picture. Okay, so how we innovated on this topic, we basically replaced the typical antenna, the 2D array of microphones, with a rotating antenna. This sensor will only have 5 microphones, but we will spin it to recreate 400 virtual microphone positions. So in this way, we have a large measurement surface, a large antenna, a lot of microphones. So we have the two performance defining parameters covered with this design. So as you see, there is an antenna. It will gather audio data, send it to a tablet, which will be your interface with the device. And it will let you also do the first analysis once you have your results. But the actual computation to go from audio to acoustical image will happen either in a laptop or on our cloud server, if you have an internet connection available. If not, you can always opt for a laptop that will do the computing on site for you. All these connections happen wirelessly, so there is no need to plug anything into anything, and the system is battery powered. It's very easy to set up with about 2 to 3 minutes from setup to measurement, and it is very easy to transport. It all fits in a compact carrying case. One more slide on the system itself, and then we can jump straight into the applications. This is the whole family setup. So we go from the smallest sensor that we offer to a larger on the right. These are all modular systems, meaning that you can simply swap one sensor for another at any given point in time. And the smaller sensor, of course, has a higher low frequency cutoff at 2.8 kilohertz, and it will mostly be used to detect leakage, so leaks in cabins, chassis, etc. The P50 will work from 700 hertz and up to detect bass, squeak, and rattle applications. So anything grinding, rattling will usually produce higher frequency noise that you can detect with mostly any camera. But when we're talking about compressor noise, fan noise, vibration, etc., the systems that will truly work are the larger array ones, the P132 or the P254. This will be a lot more precise, and they have a lower frequency cutoff, enabling much more in-depth analysis and precision. One slide on the measurement process itself. We basically need to set up the instrument, mount it on a tripod, mount the camera, rotate the sensor, and as soon as it rotates, it will start acquiring audio data. Once the recording is finished, it will send this audio data to the computer, which a few seconds to a minute later will send us back the acoustical image. And now we can start analyzing it, changing frequency ranges, changing the dynamic range of the image, showing more or less sources, etc. We will start analyzing, but we will see more on that in 1 second. So how can this help you in designing or testing HVAC products? Well, it will reduce the time for trial and error instead of, or in comparison to traditional microphonic solutions where we place a lot of microphones and try to understand based on level differences. This is a much more immediate solution. It will immediately show us where a sound source is and what its characteristics are. We can isolate different components in the machine, which is again something we cannot do with microphones alone or not in a very precise way. And of course, the end goal of all this is to increase the product quality. So we will make better sounding products, quieter products, find it easier to comply with regulations if there are any in place in your country or for your application. So those are the two main concerns: comply with regulations and make products that stand out compared to the competition. So enough on the acoustic cameras in general. Let's head straight into our first application, and we will start by an analysis of a heat pump. So what you see on the right is a typical unit. There was a problem in this case because the measured sound pressure level was 3 dB above the target set for this unit when measuring it from outside with a microphone pointing on the way of the heat pump. And so the objective here is to understand what is the problem and how to reduce or how to gain this 3 dB in order to comply with their own target. The compressor of this unit is operating at an excitation frequency of 110 Hertz, which is quite typical. A soundscanner P132 is positioned at 1.5 meters from the unit, and we simply take a 10-second recording to start understanding the characteristics of the noise that this unit produces. The initial hypothesis, because there is always something that we go off of from, is that the compressor is making the noise, and this noise is being transmitted to the case panel, and that's the final radiator. So let us take a look. We start by removing the side panel on the compressor side of the machine, as you see on the image on the bottom right. And the first image, image number 1, shows us a wideband measurement. So from 250 hertz to 6 kilohertz, all that energy is represented in that picture. We here see mainly the compressor. The dynamic range is set to 8 dB. What this means is that from red to blue, we have 8 dB of difference. And what this means in turn is that that compressor is really the main source here. It's at least 8 dB louder than any other source in this picture. We can now split the image in different frequency bands. And for instance, frequency band A goes from 250 hertz to 1.6 kilohertz, same dynamic range. And again, the main source shown is the compressor. So what this means is the compressor dominates the radiation in the low frequency range. We can now take this one step further and try to understand what the high frequency range is, or where the high frequency range is being radiated from. And in this case, from 1.6 kilohertz to 6 kilohertz, the main components are the compressor, but also a decoupling plate at the bottom of the cabinet. So if we want to deal with that noise, we also have to take into account that decoupling plate at the bottom of the unit. So we already find out some information about the sources on this side of the case, but let us go one step back and take a look at the unit as a customer. So with the panel in place, and try to understand with the functional standard unit how the noise is escaping from it. Again, image number 1 shows us 250 hertz to 6 kilohertz, but now all the noise seems to, or most of the noise seems to be coming from the bottom of the fan grill. Lower frequencies behave in the exact same way, most of the noise coming from the bottom of the hand grill, but you might also start to notice that there is some radiation by the case panel covering the compressor. Last but not least, on image B, we see again the bottom of the fan grill, but also some radiation from the fan, which is right on top of the main source, and some leakage on the side of the panel where the panel meets, on the chassis. At that joint, there seems to be some sound leakage from inside the cabinet. Another thing to note here is that the overall levels are way lower than they were before. So now we have a total sound pressure level of about 62 dBA, and before we had, rounding up 80 dBA. So there's an 80 or 70 dB difference between the two, which means that that cover is really making a good job at isolating the compressor noise. Still, even with that cover in place, we are still 3 dB over the target. Let's see another view of the unit to try to understand this fan grill problem. So we now move to the other side and take a similar recording. And in wideband, again, we understand that most of the noise is coming from the bottom of the fan grill. This is confirmation of what we already knew. No matter where we place ourselves in front of the unit, that is the main source. But there is also a contribution from the intake of the unit at the back. So that secondary source that you see in blue on the back of the unit, that's the intake, and it's also contributing. This image has now a dynamic range of 3 dB, which means that the difference from the front to the back is about 3 dB. 3 dB is non-negligible. We should also take care of the noise from the intake at some point. But the main source is still the front of the unit here at the bottom of the fan grill. The same behavior is observed for lower frequencies, and on higher frequencies, this finally changes, and now the fan is the main contributor for higher frequencies from this point of view, even though the intake is also making some noise and is visible on the image. Now, the difference is that in this case, higher frequencies are contributing about 4.5 dB less than lower frequencies, so they are not our main concern here. If we want to reduce the noise of the image of the unit, we need to work on the lower frequency range. Let us now take that panel or that grill out and try to see what's happening on the inside. And now when we're taking a look at the inside of the unit, we immediately see that the source was clearly on the bottom of the unit on the tray. uh, in wideband, in lower frequencies, but not on high frequencies. Higher frequencies are mostly being radiated by the fan, which is to be expected. But this is a strange result because there is no moving parts on the tray of the unit. So this is initially hard to interpret, but there will be a very clear explanation here. So these wires that come attached to the tray of the unit, they come from the compressor, and they vibrate. And so they are transmitting this vibration to the bottom of the unit, which in turn is radiating that vibration as sound. So let us try something to remediate this situation. You can now probably see that we have decoupled this wire harness from the tray of the unit, and immediately the image completely changed. And now the main source is not the bottom of the unit anymore, but the fan, which is a moving part. And so it is to be expected to be the loudest source from this point of view. We have reduced the total sound pressure level by exactly 3 dB, which was the target. We had a total SPL before of 63.9, and now we have 60.9 dB just by detaching those cables from the tray of the unit. So we see as that we have solved our problem. We could still improve further. And of course, these wires do not have to be dangling there forever. They can be simply recoupled to the tray of the unit with some anti-vibration measures in between in order for them to not transmit those vibrations to the tray of the unit. But now we have achieved at least the target, and we could continue to improve by still improving this transmission problem or working on some absorption inside of the unit. Well, there's many things that could be tried, but in this case, the problem was solved. I hope that you took some value from this first showcase and that this resembles what you do in practice or how you work. But in any case, don't hesitate to put any questions in the Q&A box so that we can address them in a few minutes. We can now work on an emission problem. So we will be trying to solve noise from a heat pump from the perspective of a neighboring property. So this unit is installed at a customer site. We will do two measurements in this case, one in the near field. So we will position ourselves in between the unit and the neighboring property, which is already complaining of the noise of this newly installed heat pump, to try and understand how this source radiates towards the neighbor. And then we will take a second measurement directly at the complaining property, so in the nearby house. With these two measurements, we should be able to understand if there is a problem and how to solve it, because we also need to confirm if there is actually a problem and if the noise that the neighbor is hearing is really coming from the heat pump or from something else. So in this first recording that we took directly facing the unit, we immediately see that the main source are the fans on the front of the unit, but there is also contribution from two reflections on the wall of the house. One is probably the radiation from the side panel of the unit bouncing back on the house and then coming towards us and then towards the neighbor. And the other one is the rear of the unit, potentially the intake of this unit, also emitting noise that's reflected on the wall and then contributing to the overall noise at the neighbor place. The difference between the direct sound from the fan and these reflections is about 4 dB. It sounds like a lot, but it's non-negligible. In reality, that is contribution and it should be taken into account. There are a few things that we can already propose here. Some absorbers could be placed on the wall to try to reduce these reflections from the unit. But also the unit could have been oriented differently during the installation so that the loudest source, fans, do not face the neighbor directly. So a reorientation of the unit could be a potential solution to this problem, or at least a mitigation measure. Let us see what the neighbor sees in the end. So again, this is a very short recording at about 30 meters away. We simply record for 5 to 10 seconds and immediately get these images that speak for themselves. The heat pump is exactly at the center of that of that colored area in the picture, it is contributing 35.1 dB. And the other source in the image is a highway with some traffic, but it is a secondary source. It is contributing 29.1 dBA. So indeed, we have just confirmed that easily that the noise that the neighbor is hearing is actually the heat pump, and in a lesser degree, the highway noise. So indeed, there is something to be done here in order to reduce the noise of the heat pump and at least bring it down to the level of the traffic. The overall sound pressure level at the neighboring house was 37.2 dB. The heat pump contributes 35, so yeah, most of the noise at the measurement point is coming from the heat pump. It's a very straightforward, non-ambiguous conclusion. If there is somewhere at fault here, it's the heat pump. Okay. In case you typically work with this type of scenarios, or there is a service team sent to deal with these situations when there are customer complaints on site, here is how you could approach the situation. We will go now to a bit of a more complex scenario. There is a simple objective, which is to understand the main sources on this automotive HVAC unit. So this is to be installed in a car. And the idea is to understand what the sources are, to try to mitigate them, but there is no clear target like in the first case. We will be using the P254 sensor in this case. This one goes down to 125 Hertz, so it can measure very low frequencies for acoustic cameras. And it will also be extremely precise at any given frequency, so it can really distinguish between sources which are very close together physically. We place the unit as close as we can to the sound scanner, so 60 centimeters away. We have the chance of dealing with an anechoic chamber here, which just makes things better, but it's not a requirement whatsoever. We have plenty of customers measuring in non-treated rooms, or as we saw just before, on site. And yeah, we will leverage the high spatial resolution of this unit, of this sound scanner P254, to try to study this HVAC. So we take a first picture. This again, stabilized condition. We make it ventilate and we measure the noise for 5 to 10 seconds. In wideband, so if we consider the whole spectrum of this measurement, we immediately see that most of the noise is coming from the right-hand side of the unit. And we would typically now start using filters, as we did before, to separate the spectrum in different bands and understand which component is radiating which band. Unfortunately, with a complex machine like that one, this can be a pretty tedious process. There are many peaks here. We would need to place filters around each one of them, and this could take some time. But there is a more straightforward approach, a faster and more efficient approach that our system will let you use. And that basically consists on drawing selection boxes. We call them regions of interest around components on your machine. If you already know the machine by design, you know which are the main potential noisy components. In this case, the manufacturer of the unit selected these three. He thinks that these are the three main areas that can produce noise or distinct noise. So we simply make a selection, and now the system will calculate the spectrum corresponding to each selection box. So we'll now get a separate spectrum curve for each of these regions of interest, 1, 2, and 3, denoted by the colors orange, yellow, and purple. Okay, so once again, on the top left, we have image number 1, full band. It's the exact same one that we had seen before. If we focus on the top right, we have the frequency spectrum for each of these regions of interest. Of course, in the software, we can zoom in, but in this presentation, it's a bit more complicated. But we can immediately see that the curve, the orange curve around region C, is way louder than all the other curves. So we already know that region 1, the orange one, is much louder than the others, between about 2 and 3 kilohertz. That's quite immediate. There are other areas where the yellow curve is higher than the others. If we look around 3,400 hertz or so, we immediately see that that yellow curve is higher than the others, and same from 5 kilohertz and up. And between 1 and 2 kilohertz, we also see that the yellow and purple curves are higher than the orange curve. So now we can start placing filters as we did in the first example, but knowing what to expect. So if we place a filter in region A, in frequency region A, so from 125 hertz to about 750 hertz, we obtain the image A. And this image shows very clearly that the main source in that frequency range is region of interest number 3, so the bottom component, bottom right component. If we now take a look at frequency region number B, we can immediately see that this is mostly radiated by the zone 2 on the top right of the unit, and in a minor degree by region of interest number 1, the orange one. Now, if we go to region C, as I advanced in the first part of this slide, this is absolutely coming from side 1, and we understand that these particular frequency contents come directly from the area number 1, denoted by the orange box. So now we have managed to understand which of these components radiates which frequency range. We could still push this analysis much farther and make it with smaller selection boxes. If you're interested in a specific harmonic, if you want to improve the psychoacoustic characteristics of the unit and the noise is very tonal, we can go to those tones and try to understand where they are being radiated from. We can also subtract the curves and more easily see which one dominates in which frequency band. So yeah, in this case, we subtracted region 1 to region 2 and 3, and we get the corresponding difference curves. So all the high frequency range is largely dominated by region number 2. Lower frequency ranges, it's pretty much shared between region number 2 and 3. And of course, region number 3 dominates in this mid frequency range. So as a small recap before we finish this presentation, what these tools enable us to do is to unambiguously identify the root cause of a noise problem. So instead of working with microphones and not being absolutely certain of what the problem is, where it's coming from, and what its characteristics are, in this case, it's very immediate and direct, and there is no doubt after a certain amount of measurements of what the problem actually is. This enables us to work a lot faster, but it's important to also note that it will enable us to communicate our results and solutions a lot better. So if management or a customer or interested parties need to be involved in the process, they will be able to understand acoustical images a lot better than your traditional metrics, sound pressure levels, curves, spectrums, etc. Last but not least, this will also let us pretty easily document the efficiency of these measures. So if we have a certain solution to our problem and we implement it, we immediately can see with the camera if this is making an impact or not. I see that there is already a raised hand. I will wrap this up. Thank you very much for your time. I hope that this presentation was valuable for you. I hope that you learned something. And I will be more than happy now to answer your questions and have a quick conversation. Thank you very much. Okay. Yes, so I have just unmuted the participant that was willing to ask a question. So you can simply ask it, or I can reply to the typed question. Okay, so the first question is, what is the cost of each type of noise camera? I can easily share a price list right after this presentation. The cost ranges from 5,500 euros for the smaller systems to 9,500 euros for the more advanced cameras like the P254. everything in between, we have something for you. You have to also consider the software license for these cameras if you want to go into the advanced features. But yeah, I will easily share a price list after the presentation. Yep. Any other questions? Okay, let us wait for 1 or 2 more minutes in case people are still thinking about their questions. Okay, I just had one more. So someone is asking if this can work with larger installations, larger machinery. The answer is yes, of course. As we've seen, we can make measurements from a far distance. So you can go as far as you need in order to make the machine fit inside of the image and make your analysis on even larger machines. Absolutely possible. The farther away we go from the machine, the lower the resolution. So it is always better to try to get as close as possible as long as we fit the whole machine into the field of view. But yes, indeed, we can go. We have made measurements up to 250 meters without any problem in the case of environmental noise problems or noise disputes. Okay, if there are no more questions, I will now end the webinar. I thank you very much for your participation and hope that we can stay in touch. And yep, thank you very much.